Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to this week's class of Advanced Digital Communication in MSc Telecommunication Engineering program at the Department of Telecommunication Engineering, University of Engineering and Technology, Mardan. This is your course instructor, Dr. Naveed Mufti. And the main topics for this week are correlation receiver, probability of error, and the error performance analysis. So last week we looked at noise and communication systems, signals and noise. Within that topic we looked at error performance degradation in communication systems, demodulation and detection as the two main steps in digital receiver, a vector view of signals and noise to have a better understanding of how noise affects signal vectors. Then we discussed the basic SNR parameter for digital communication systems, which is a normalized version of SNR known as EB by N naught. And then we looked at the detection of binary signals in Gaussian noise. And in the end we discussed error probability indicated by PB. And finally we discussed the match filter. Okay, so in this part of the lecture we will be looking at the correlation realization of the match filter and how we can optimize the error performance, and then we will be looking at the correlation receiver and the concept of binary decision threshold, followed by a little bit of discussion about the differences between coherent and non-coherent detection, and then a comparison of the bit error performance for various modulation types. Lastly, we will be looking at Emery signaling and their performance. The learning outcomes for this part of the lecture are as follows. Students should be able to display an understanding that match filter or correlator is the most optimum choice for maximum SNR and minimum probability of bit error. Choosing the best threshold for detection. Demonstrate an understanding of working of the correlation receiver. Understand the detection problem. Differentiate between coherent and non-coherent detection. Compare the error performance of various modulation schemes. And recognize that EB by N naught is not the only performance comparison parameter for Emery signaling techniques. So a quick recap of the match filter. As we have discussed last week, the match filter, it provides the maximum signal to noise ratio at its output for a given transmitted symbol waveform. And the expression that we derived was that the maximum value of signal to noise ratio at the sampling time capital T is less than or equal to 2E by N naught. And this inequality is equal when the transfer function of the system is of this form, as I have shown here. This was also shown last week, and the transfer function is of this form here. And when we look at it in time domain, this basically means that the impulse response of the channel is like this within the signaling interval. So it means that the impulse response of a filter that produces maximum output SNR is basically the scaled version of the message signal, getting multiplied by a constant k and delayed by the symbol time duration capital T, like this. We also simplified it even further by saying that the channel's impulse response is basically just a delayed version of the message signal. So here it is graphically explained. For example, if S of t represents your signal waveform, so its negative will be its mirror image about y-axis, so it will look like this. And then if we introduce a delay of symbol time duration capital T, so this will basically show a shift and it will look like this. So this graphically and mathematically it is written as this. This is the wanted impulse response of the matched filter. So that is what we want, a matched filter. Now we come over to the correlation realization of the matched filter. So first of all, the figures that we have seen on the previous slide, they illustrate the matched filter's basic property, that the impulse response of the filter is a delayed version of the mirror image of the signal waveform, as we have discussed. So the output Z of t, as indicated here, this output, the output Z of t of a causal filter, can be described in the time domain as the convolution of a received input waveform R of t with the impulse response of the filter. So that is how we can define Z of t. You have studied signal systems, so you know that that is how we can represent the output coming out after the matched filter. Okay, so basically this becomes the equation, and the convolution that can be written as an integral. So in this equation, if we substitute h of t from the previous slide, the expression from the previous slide, and if we substitute that into h of t minus tau, and we assume that the constant k is unity. Okay, so after this substitution, this equation, it changes into this, and when we open the brackets, then it becomes this. And when t is capital T, yes, we can write this expression as this. So basically they both cancel, and this is what we are left with. So what is this thing? Yeah, so in all this expression in derivation, just remember that Z of t, it represents the output of the causal filter. So this, the final expression we have, Z of capital T, that is the product integration of the received signal with the replica of the transmitted waveform over one symbol interval. This is what is called correlation. So this is basically the correlation of R of t with S of t. So this is basically the start of the correlation realization of the matched filter. We continue our discussion of the correlation realization of the matched filter. So let us consider that the received signal R of t is correlated with each prototype signal Si of t, where I is equal to 1, 2 up to m. So if our signal can be any one of the m signal waveforms, our received signal is basically correlated with each prototype signal. And that we do by using a collection or a bank of m correlators. And then the signal Si of t, whose product integration or correlation with R of t yields the maximum output Zi of t, that is the one, that is the signal that has the best match with R of t as compared to all the other prototype waveforms. So one will have the best or the maximum value, and that is the one that is selected by the receiver, assuming that it was the one that was transmitted. So it performs a correlation with all the prototypes, and then based on the maximum value of the correlation numerical value, it selects the one with the maximum value and assumes that that was the one that was transmitted. So it is similar to that minimum distance concept that we studied when we looked at signals in the vector space. And this is the background that is used for optimum detection of signals. We already have that background, you have that graphical picture in your minds, and mathematically that is how it is being done. So as I said, we have to optimize the error performance. So to optimize or minimize the probability of error in the context of an AWGN channel and the receiver shown here in this figure, we need to select the optimum receiving filter in step 1. We need to select an optimum receiving filter here and an optimum decision threshold here. So here I am giving you two different examples for comparison. So the two things we need to do is to decide an optimum decision threshold in step 2. Yes, and for binary case we've already discussed that. And then we have to also select the optimum receiving filter in step 1. So we have to choose the match filter because that maximizes SNR. So basically what we need to do is to maximize the difference between the possible signal outputs. Okay, so when we maximize their difference, basically we maximize our SNR or our capability against noise. So which means maximizing A1 minus A2, which means maximizing the difference between the values of A1 and A2. So that means the further apart A1 and A2 are, the greater is the difference between them and greater is the SNR. So previously we discussed that the match filter was described as the one that maximizes the output signal to noise ratio for a given known signal. Here we continue that development for binary signaling, where we view the optimum filter as the one that maximizes the difference between two possible signal outputs. Okay, so what you have to remember is that now we are trying to maximize the difference between the two possible outputs. And now if you look at these two figures that I have shown, you've got this choice. So let's say this is A1 and this is A2, or you've got this choice. So which has greater distance? What do you think? The distance between these two is greater, or the distance between these two is greater? So wherever the difference is greater, we will have a better or a higher value of SNR as compared to the other case. So clearly it shows that this case is better. Now what is this case? This is the case for orthogonal signals, and this is the case for antipodal signals. So if noise is the only degradation, we know that our received signal is basically our transmitted waveform combined with noise. So given this R of t, our detection process has two steps, as we know, this and this. These are the two steps. In step 1, our received waveform is basically reduced to Z of capital T here. So in this step we are transforming a waveform into a point in decision space, and in step 2 the simple decision is being made, which is based on comparing our sample value, that of capital T, to a threshold. And basically what it translates into is that in which decision region the point is located. So with this background, for the detector to be optimized, it is necessary to do certain things. If we want to optimize it, we have to optimize this step. We optimize the waveform to sample transformation, and we use a match filter or a correlator in step 1 for that. And then we optimize the decision criterion in step 2. So by optimizing both steps, basically we optimize our receiver design, or we optimize our correlation receiver. So from previous knowledge, we know that the match filter, it provides maximum SNR at what time? It provides maximum SNR at the filter output at the time t is equal to capital T. That's what we remember. And then we have, as we have discussed in the previous slides, correlator is basically a realization of the match filter. So as we know that to correlate means to match, so we can define a correlation receiver as consisting of m correlators, and it transforms the received waveform R of t to a sequence of m numbers or correlator outputs, and then the correlators, they attempt to match the incoming received signal R of t with each of the candidate prototype waveforms, and these waveforms are known a priori to receiver. So basically this is the background of the correlation receiver. And the correlation receiver, if we look at it graphically, this discussion on this slide, if we look at it graphically, basically each correlator output is characterized by this equation. So we've got m correlators, so I goes from 1 to m, and there is an output corresponding to each correlator, and that output is governed by this equation here. That is the equation we derived previously as well. So as you can see, the I keeps changing, so R of t is basically correlated with every prototype waveform, so there is an answer to every of this equation, and in the end we have few values to compare, and the decision rule is that we will choose a waveform Si of t that matches best, in simple words, or we can say the one which has the highest correlation with R of t, or the one whose index corresponds to the maximum value of Zi of t. So this is what it looks like. So the received signal is then first multiplied with the reference signals. So we have all the reference signals here known to the receiver a priori, and once we multiply our received signal with the reference signal, then we integrate it. So this implementation is represented by this equation, and then that's the output. So that's the output for the first correlator, similarly second, third, fourth, that's the output for the mth correlator. And once we have all the outputs, we have a decision stage where the comparator, it selects the Si of t with the maximum value of Zi of t. So, and then decides in its favor that that was the waveform which was transmitted. So considering that case for a binary detection receiver, so for binary, our m correlators where m is equal to 2, so we will have basically two reference signals, S1 of t for 1, S2 of t for a 0, and whatever signal we are receiving, that will be first multiplied, the product, and then integrated. So we will have two values to compare, Z1 of t and Z2 of t. So we will compare them, and then the correlator or the decision stage will decide in the favor of one of them. So either we can have for binary, either we can have a receiver design in that way, which involves having two correlators. This is one and this is the other. Or we can have our correlation receiver configured as a single matched filter or a product integrator. So if that's the case, when we are using a single correlator or a product integrator, then we need to do is that instead of the specific individual signals acting as reference, the different signal acts as our reference, the different signals. So, and then our received signal is multiplied by the different signal, and then a decision is made on whether that is greater than the threshold or less than the threshold. So the difference between these two configurations is obviously that here two matched filters or product integrators are used, here one matched filter or product integrator is used, and the end result is the same. Ultimately we have to make a decision, and that decision will either go in favor of S1 or in favor of S2. So these are two different ways of implementing the correlation receiver for binary detection. So coming over to the discussion on the binary decision threshold. So we have looked at this curve previously as well. So this figure illustrates two conditional probability density functions, probability of Z given S1 and probability of Z given S2, with mean values of A1 and A2 respectively. And these PDFs, they are also called the likelihood of S1, this one is likelihood of S1, and the likelihood of S2. So they have been previously discussed, and we've also discussed their mathematical equations, So this is the equation for this PDF, and this is the equation for this PDF, and you can see that their shapes are very similar, symmetric, but they are different in their mean values, as shown here in this equation as well. And then we are looking at our decision making criterion. So here in these equations, once again, this sigma naught represents the standard deviation, and it's a square that represents the noise variance, and this rightmost likelihood, it illustrates the probability density of the detector output Z of t given that S1 was transmitted, and this likelihood function, it illustrates the PDF of Z of t given that S2 was transmitted, and the abscissa, this x-axis here, that represents the full range of possible sample output values from the correlation receiver. So with reference to optimizing the binary decision threshold for deciding in which region the received signal is located, so we discussed previously that the minimum error criterion for equally likely binary signals, if it is corrupted by Gaussian noise, the optimum threshold value can be given by this equation, where A1 here is the signal component of Z of t when S1 is transmitted, and A2 is the signal component of Z of t when S2 is transmitted. So the threshold level gamma naught, which is represented by the mean or the average of the values of A1 and A2, that becomes the optimum threshold, which will minimize the probability of making an error or an incorrect decision, given that the signals are equally likely and the likelihood curves are also symmetric. So what was the decision rule? Based on this, what decision rule we can conclude? It states that hypothesis H1 should be selected, or in other words, deciding that signal S1 of t was sent if Z of t is greater than gamma naught. And hypothesis H2 should be selected, which is equivalent to saying that S2 was transmitted if Z of t is less than gamma naught. If Z of t is equal to gamma naught, then the decision can be an arbitrary one and it can go in any symbol's favor. So if we have, in this case, if we have equal energy and equally likely antipodal signals, antipodal, with the signals are in amplitude wise they are the same, but they have 180 degrees phase difference. So for antipodal signals, S1 of t is basically the negative of S2 of t, which means that A1 is the negative of A2. Then this optimum threshold rule, we apply those values here. If we put those values here, then that is what we get. We are basically comparing to the value of 0. So in this case, we will decide S1 of t if Z1 of t is basically greater than Z2 of t, and we will decide in favor of S2 of t if Z2 of t is greater than Z1 of t. So coming over to detection techniques, basically there are two main types of detection. One is called coherent detection and the other is called non-coherent detection. And the primary difference between these two is the presence or the absence of phase recovery circuit. So what is a phase recovery circuit? A phase recovery circuit is used to have a local generated carrier wave at the receiver synchronized with the oscillator at the transmitter. So basically there is some piece of hardware at the receiver which tries to detect the phase of the incoming signal, and the idea is that it wants to match or log the phase of the incoming signal with the local oscillator in order to achieve synchronization with the oscillator at the transmitter. So that's a major difference between these two types of detection. Now in coherent detection, as I have explained, it requires a replica carrier wave of the same frequency and phase at the receiver as exists at the transmitter. Now that is a big challenge, or we can say that the local carrier generated at the receiver has to be phase locked with the carrier at the transmitter. So both the oscillators, they need to be synchronized in phase and frequency both. So the received signal and the replica carrier signals, they are cross correlated, and this is something which is also known as synchronous detection. So we will receive a noisy signal, and we will try to generate some carrier signals locally, and then we will try some sort of a cross correlation in order to come up with this coherent detection. So you can expect that match filters or their equivalents are used, and because it involves phase matching or phase detection or phase locking, so you can expect some sort of phase lock loops or similar hardware in coherent detection circuits. Coming over to non-coherent detection, the first thing we need to remember is that no attempt is made to determine the actual value of the phase of the incoming signal. That is, phase lock is not the target, so it is not attempted. So it requires no reference carrier for phase lock. Obviously this makes it less complex than coherent detection, but we have to remember that the error probability in non-coherent detection is higher than coherent detection, and so its performance is not as good as coherent detection. But because its hardware is simple, so you can expect envelope detector or similar hardware in the receiver structure of non-coherent detection. So we have compared both types of detection, and one of them is used, and based on the hardware you can have a guess as which type of detection is being done, whether coherent or non-coherent. Now coming over to comparison of bit error performance for various modulation schemes. So I am showing you a table here. This table has different values of probability of bit error for different modulation schemes. So these are basically the PB expressions. These are the PB expressions for the best known of the binary modulation schemes, and for PB is equal to 10 raised to the power minus 4. It can be confirmed that there is approximately a difference of 4 dB between the best and the worst of these schemes that are being shown here in this table. And if you look at these expressions or these value, you can conclude that the best one is coherent PSK, this one, and the worst one is orthogonal FSK, the non-coherent orthogonal FSK, this one. So there is a difference of almost 4 dB in these two schemes. So in some cases 4 dB is a small price to pay for the implementation simplicity gained in going from coherent PSK to non-coherent FSK. However, in many other cases even 1 dB saving is worthwhile. So what you have to remember that there may be other considerations besides PB and system complexity. So for example, if you have a channel with a lot of fading, a non-coherent system may be more desirable or more suitable, because in such situations you might find it hard to establish and maintain a coherent reference between the local oscillator and the transmitter oscillator. So just remember that there might be other considerations. However, when we compare these selected binary modulation schemes based on the expressions for probability of error, so we will go for coherent PSK. Now coming over to our discussion on Emery signaling and performance. The first thing that we should be clear about is this curve, which is the curve of probability of error versus EB by N naught, our normalized SNR. So the typical probability of error versus EB by N naught curve will have a waterfall shape. So the probability of bit error characteristics of various binary modulation schemes in AWGN will show a similar shape, a waterfall shape. But what should an ideal PB versus EB by N naught curve look like? So this figure here, that also shows you the ideal curve, ideal characteristic, which is based on the Shannon limit, and this limit represents the threshold EB by N naught, below which the reliable communication cannot be maintained. So we've discussed Shannon already. So based on a derivation of Shannon's channel capacity theorem, basically we reach this value of minus 1.6 dBs. So we can describe the ideal curve in this figure as follows, that for all the values of EB by N naught above the Shannon limit of minus 1.6 dB, PB is 0. Once EB by N naught is reduced below the Shannon limit, the PB it degrades to the worst value of 1 by 2. So it should be clear by comparing the typical PB curve with the ideal one that the large arrow in the figure describes the desired direction of movement to achieve the improved PB performance. So as we move along this direction here, that is an improved error performance, and as we move along this direction here, that is a degraded error performance. Okay, so let us continue our discussion of Emery signaling and performance. And here in this figure we are looking at different curves. As you can see, bit error probability PB on y-axis and EB by N naught on x-axis, and now instead of one curve we have multiple curves. So we have the bit error probability for coherent schemes, coherently detected Emery orthogonal signaling. So all of them, they are basically different levels of Emery orthogonal signaling. And as you can see, as k increases, where m is equal to 2 raised to power k, so k is basically, you can say, the number of bits. So as k increases, the curve it moves in the direction of improved error performance, as you can see here. So it is approaching the ideal curve, that of Shannon. So it is going in the direction of improved error performance as k increases. But here in this figure, now that is the curve of PB versus EB by N naught for coherently detected multiple phase signaling. So here we had orthogonal signaling. Here we don't have orthogonal signaling, but multiple phase signaling. And as you can see, as k increases, now we are going in this direction. So basically, as k increases in this curve here, the up arrow, the curve it moves in the direction of degraded error performance. So now we have a conflict. If you look at this curve for orthogonal signaling, as k increases, we are improving our error performance. But if the signals are non-orthogonal, as k increases, the curve starts to move in the direction of degraded error performance. So Emery signaling, it improves better error performance when we use orthogonal signals, and degraded error performance when we use non-orthogonal multi-phase signaling. So that is what you have to remember. So the question is, why would anyone ever use multiple phase PSK signaling if it provides degraded error performance compared to binary PSK signaling? So as we saw in the previous slide. So if orthogonal is better. Just like in BPSK, we have orthogonal signals. Yes, if you remember the constellation diagram, we have orthogonal signals. So why would anyone prefer multi PSK if its performance is not good as binary PSK? So what you have to remember that EB by N naught is not the only performance criterion. What about the required system bandwidth? So if you compare the performance of these two schemes in terms of bandwidth, what will you say? So for Emery orthogonal signals, as k increases, the bandwidth also increases. But for Emery multiple phase curves, as k increases, so we can accommodate or we can achieve larger bit rate within the same bandwidth, or if we are keeping the data rate constant, then we need lesser bandwidth. So actually with multiple phase Emery signaling, as k increases, the bandwidth requirement decreases, but with Emery orthogonal signals, as k increases, the bandwidth requirement increases. So that's where the difference is. So not considering anything else, just EB by N naught and bandwidth, so we have a trade-off. We have to make a choice or a balance. If you want to go for orthogonal signaling, we will have a better error performance, but we have to compromise on bandwidth because we'll need a larger bandwidth. So better error performance at the price of larger bandwidth. Or if you want to go for Emery multiple phase signaling, we will have a better bandwidth performance, but that will come at the price of degraded error performance. So it's a compromise. You have to, if you want to improve one thing, the other thing will have to be compromised. So that's what we have to remember. So in the last, I would like to sum up by discussing the effects of ISI, because in our recent discussion over the last 2 weeks, what we did was that we treated the detection of signals in the presence of AWGN. And if you remember the impulse response equation for Z of t, so even there, or if you remember our discussion, we assumed that there was no ISI, so there was no degradation due to ISI. So that was a simplifying assumption, because in practice or in real scenarios, ISI will also be present. So we have studied what ISI does. Yes, ISI can degrade error performance also. If you remember, we compared two curves where in one system increasing the EB by N naught did not improve the error performance, whereas in the other scenario it improved the error performance. So when ISI is present, we will have additional error performance degradation, and that degradation can come in both coherent and non-coherent detection schemes. So what you have to remember that when we are including both noise and ISI, we will have a degraded error performance even further. So that is a subject of research, and that will happen. So just remember that when we include the effects of ISI, the error performance will further degrade as compared to just only considering noise without any ISI. So this brings us to the end of this week's lecture.